Finding birds and trees.
Yeah, yeah.
Yep, we're ready to go? Sure. Okay. Well, hello, everyone. Welcome to Orchestra Hall. I'm John Mann, Director of Education for Lakeside. And for this afternoon, we're fortunate to have Dr. Phil Stahl as our speaker. And today, Phil will be presenting a session titled, Are We Alone? This is a question that motivates NASA's next large flagship mission, the Habitable Worlds Observatory, as well as smaller precursor science missions, such as the Planetary Origins and Evolution Multi-Specular Monochronometer mission. This presentation reviews the science of planetary system formation and the search for planets and life, and discusses potential mission concepts and telescope engineering needed to accomplish this science. Phil is a recipient of the NASA Distinguished Service Medal and is currently a senior optical physicist at NASA Marshall Space Flight Center. I would ask if you would please mute your cell phone ringers if you haven't already, and help me in welcoming Phil back to Orchestra Hall.
And I just muted my own. So, how many of you guys have not seen me give a talk? Oh, wow. Okay, so I guess I had to introduce myself. If you'd all seen it, I wouldn't have to repeat. So I grew up in Bellevue. Anybody know where Bellevue is? A few of you. So I grew up in Bellevue. Any of you come up like from Columbus or somewhere south up Route 4? When you go up and over the railroad pass, if you look off to the right, that's my family farm. It's been in my great-grandfather bought it in 1895, I think, ish. So we've been there a while. My great-grandfather actually it's my great-grandmother who owned the cottage over here on Park Road, that Stone's Throw Cottage. Anybody know Stone's Throw Cottage? Yeah. So they had the cottage there before the fire of 1900, and then they rebuilt, and they built that cottage. And so my grandfather, so let me back up. So this is New England, right? This is the New England week. So I'll back up a little bit further. Is my grandmother, who owned that cottage, grew up in Newtown, Sandy Hook, Connecticut. Her last name is Mitchell, and her ancestor came over into Cambridge, Mass. In the 1600s with the first load of cattle. And the Mitchell farm over on the Nagasaki River, it was founded, I think, in 1768. And her father was Deacon Mitchell of the First Congregational Church of South Britain. And she went to Oberlin, where I think she completed an entire year of college. And then my great-grandfather, who's the Stahl side of the family, we came out of France, Alsace-Lorraine, Buffalo, came down into Ohio in the 1800s, 1830-ish. Anyway, my great-grandfather went to Oberlin, took a semester of classes, and came home with a wife. And they did fairly well. My grandfather actually went to Oberlin preparatory school, which is high school, and came home with a wife who while he didn't go on to college, she actually, I think, was one of the first female graduates of Oberlin. She completed her 4-year complete. So there we got a New England connection in there. And actually, so on my mom's side, we're descended from Governor Thomas Wells, who's the only person, I think, who served in all 4 administrative capacities of the Massachusetts Bay Colony in the 1600s, of governor and so anyway, I forget. Oh, so coming back to the future, I grew up in Bellevue. I went to Wittenberg. I'm sure there may be some Wittenberg people in the room. Did my undergraduate in physics and mathematics at Wittenberg, and then I went to graduate school at the University of Arizona. And frequently there's a Tucson person in the room sometimes. There was our Tucson people. Are you the people that know Bob Bro? No? Bob Bro? No, there's a guy from Tucson who's a pilot, and one of my bosses in Tucson was a pilot, and they've served with each other in the Vietnam War, and it's a really small, 7 degrees of freedom, right? So anyway, Tucson here. I currently live in Huntsville, Alabama. We have a couple of cottages up here, up on Jasmine. The most recent one we did. Anybody know Sid Foster? No. So Sid was on 136, the White House on Jasmine, that we bought and renovated it. And my kids went to Miami and Denison and Wittenberg. So there we go. So as John was saying, NASA is governed by these questions. How did we get here? Which is about the beginning of the universe, the evolution of the universe, the formation of stars, galaxies, and global clusters. And I talked about that a little bit in May. And a lot of that is with regards to James Webb Space Telescope data. Oh, I guess that's the other thing is I was responsible for making the mirrors for the Webb Space Telescope, and I signed off the document that they meet some specifications. As explained to me, my job is to make sure we didn't have a Hubble problem, which we did. It works great. Where are we going is about whether the universe is going to, how will the universe end? Will it just keep going forever, or will it collapse back down? I don't work in that area. I don't know much about that. And then the third question is, are we alone? Is a very compelling question. Is there life in other planets on the, are there other, first off, the question was, are there other planets? Which we now say yes. And then, might there be life on other planets? So that's one of the things we're going to go look for over the next 20, 30, 40 years. It's going to take a while. But it's a very compelling question. 10, 20 years ago, I was going all around the world giving lectures on the plans for the Webb Space Telescope, and one of the questions, that kept coming up, no matter where I was, is there life elsewhere? In fact, famously, former President Obama got in a little trouble for saying that, oh, definitely there's life elsewhere. He just hasn't seen it yet. I think he's a little overconfident. So before I get into that, one of the key things to understand about exoplanet science is spectroscopy, and that every element in the periodic table has a unique spectra, a fingerprint. So by looking at the colors of light that we collect with our telescopes and our instruments, we can figure out if a planet has oxygen or hydrogen or nitrogen or sodium. And in fact, if you set up a spectrometer and a little diffraction grating, you look at a fluorescent light, you're going to see a lot of spectral lines in the fluorescent light based upon the chemicals that are in the light bulb. There are different ways to get spectra. If you were to just take a diffraction grating and look at incandescent light bulb, it's a thermal heat, it's just a continuous rainbow. So it's sort of like the rainbow in the sky is a continuous rainbow because the sun is a thermal source. But if you take sunlight and you run it through a cloud of gas, that gas will absorb wavelengths of light based upon the chemicals in the gas, and then you can get a spectra, and you look at those lines, and those lines tell you what is inside the gas. Or you can look at the light that gets emitted out of the gas, and you can see lines there. So this is how we can figure out what's going on. By the way, so this laser pointer, I'll back up. I'm an optics PhD. This laser pointer says it's a class 3. Okay, if you ever see a class 3 laser pointer, never point in your eye. It'll burn a hole in your retina. Particularly because this is green light and your eye is most sensitive to green light. So don't ever let any little kid point a green laser, class 3 laser into your eye. The red ones, by the way, if they're class 1, it's pretty safe. If you put a class 1 and point it in somebody's eye, they're going to close their eye before it does any damage. But kids playing with these green ones, don't let them. It's okay for you guys because, see, when I put it up there, it's scattering and makes it really bright. So it's great for a pointer, not a toy. Laser safety. Safety first. Okay, so the first exoplanet we identified was in 1995. It's a very famous peg. A Nobel Prize was awarded for the team that found that exoplanet. Since then, we are well over 6,000 exoplanets, hundreds of which are Earth-size, and the field is just growing exponentially. The first exoplanets were found with radial velocity, and so then we grew, and then we've developed the transit method, and so we keep developing new technologies on how to find more and more planets. So this is the radial velocity method, is that if you have a big planet orbiting around its star is going to wobble back and forth. And if you think about the Doppler effect, you know, with the race car, when a race car goes, or if you hear an ambulance go by and you hear the siren change pitch, it's the same thing, is that when the star is moving away from us, the light gets shifted one direction in color. When it's moving towards us, it gets shifted another direction in color. And so we can tell by seeing that shift that there's something moving that star back and forth. And if there's something moving that star back and forth, it's got to be something like a big Jupiter. So if you have a big Jupiter orbiting a star every few days, it could shift things around. So here's the example. And so there's the wavelength going red, and then it'll go towards the blue. And so again, we're looking at the spectra of the light coming off of the star. We're seeing that it's shifting in say, a 1 day or a 2 day or a 5 day period, which tells us how close that big planet is that's orbiting it. The limit of where this technology is maybe 5 times the size of our planet, 5 times larger than Earth. An AU is an astronomical unit. Earth orbits at 1 AU. We're pretty well self-centered. Everything revolves around us, so we define the astronomical unit to be our distance from the Earth to our sun. And so this planet is about 5 times bigger than Earth, and it's got an orbit somewhere in the habitable zone, potentially. And this was measured with a spectrograph on a 3.6 meter observatory in Chile. This one is 4 times the size of the Earth. It's the second planet found around the star using the radial velocity. And I put the dates when this information was published. This was published in October. All right, the next curve, if you remember, the biggest growth was in the transit method. And this is the way the transit method works, is when a planet passes between our telescope and its star, the brightness of the star dips. And the size of the dip is proportional to the size of the planet. And so as the stars go round and round, they build up this profile of brightness, and then we play some mathematical games and decompose it, Fourier decomposition, and we can figure out how many planets there are and what their period is and what their size is. The Kepler mission was launched in '09. It's stared at a small patch of sky with thousands of stars and monitored them constantly for dips in their brightness curves in order to find, and so Kepler's found over 1,000 confirmed planets and another 4,000 potential planets. And this is what the real data looks like. You can see it's very noisy. It's very noisy. And this dip, look at here, it's 0.0005%. So that's 0.05%. It's a very small number. It's a very precise measurement. Here's some examples of the Kepler. So the Kepler-11 was a star similar to ours, and it has 6 mini Neptune-sized planets. So here's our solar system. There's Venus and Mercury. Here's Kepler-11 with all of those 6 planets in close to its star. This is Kepler-22. This was the first transit method that was found with a planet in the habitable zone. And I'm going to talk about what the habitable zone is a little bit further. But so again, this is our solar system here with Mercury, Venus, Earth, and Mars. And this is Kepler-22 with a planet that's in its habitable zone. All right, Spitzer did a transit method and found this star system called TRAPPIST-1. The science team that did this observation was from the Netherlands. Big fans. Anybody been to the Netherlands? Anybody been to the Trappist brewery? Actually, I should say, anybody been to the Trappist monkery? Yeah, so the Trappist monkery has the Trappist monks brew some very fine beer called Trappist beer. So the Netherlands team named this planetary system after their favorite beer. So this is the Trappist system, and you can see here, this is our system, and this is where the Trappists are. The one thing about the Trappist system is it's an M-dwarf star. Our star is a G-class star. Our star is a very vanilla, run-of-the-mill average star at about 6,000 Kelvin. Very, very hot, but at that temperature it glows yellow. You can have a K-class star, which is hotter, and its peak temperature is going to be in the blue. These M-class stars, their peak temperature is 2,000 to 3,000 degrees Kelvin, and their peak temperature is in the red. So these are red stars. They're dwarfs. They're small stars. There are lots and lots and lots and lots of M-class red dwarf stars in our galaxy. It's the most common type of star, and that's why the astronomers like to look at them. But it's a terrible star to look for life because they're very violent. They put out solar flares all the time. And so if you have a bunch of planets in here close to a star that's erupting constantly with solar flares, it's basically blowing away the atmosphere, sterilizing the surface on a regular basis. So it's highly unlikely we'll find life on an M-class star system. Okay, so this is how Spitzer observed the TRAPPIST system. This is the actual data. So all these things, that's a 5 or 6 day observation. So they're really zipping around. They're really close in and they're moving really fast. So the TRAPPIST, one of the things is that with the transit method, remember I said that is that as light goes through a cloud of gas, you can see what it's made up of with the cloud of gas. So if a planet has an atmosphere, when the planet moves in front of its sun, if there is an atmosphere, it'll absorb some of the light coming from the sun. So we can look at the spectra of the sun with and without the planet, and we can figure out if the planet has an atmosphere. We can also look at the spectra of the planet when it goes behind the sun to look at the light that's getting reflected off of the planet to see if it has an atmosphere. So one of the things that we did with Webb is we looked at the eclipse of what the spectra looked like when the planet went behind its sun. So this is the spectra with and without the planet, with sunlight only, and this is, you know, the star with the planet. And its spectra has basically no structure, so we determined that this planet does not have an atmosphere. Or actually, it could have an atmosphere, but it could be like a Venus. In other words, Venus looks the same all the time. So this is a planet that looks the same all the time, so it either has no atmosphere or it could be a Venus. This is another Spitzer star system, and this one is much friendlier towards us. It's a young star system, about 10 light years away. It has an asteroid belt. It has a Jupiter. So this is our source. So here is us. There's our Jupiter, and here is Epsilon. And you can see it has something that might be out there around Jupiter. It has an asteroid belt. There's probably inner stars in here. And this is also then our star system here. There's the Kuiper belt, Neptune, Jupiter. And then this is its comet belt, and it has a couple of planets. So this star system could be similar to our own. So how do we detect planets directly? Well, you have to block the light from the star in order to see the light that's scattered off of the planet. But the stars are a billion times brighter than the planets. So you have to knock down, you know, you got to reduce the starlight by almost a trillion times. So this is one way to do it. It's called a coronagraph. You put it inside of the telescope. And this is the baseline method that they're looking at for the Habitable Worlds Observatory, or we're looking at for the Habitable. So first off, you make an image of the star, and then you put a dot. And you block that star, and there's scattered light, diffracted light, and you go and you knock that out. And then the planet light comes in, and it goes around the outside of the dot, and it forms an image, but it's very dim. And so now what you got to do is you crank up the contrast, and it looks really low, and then you use something called a deformable mirror to correct minute nanometer, fractions of a hair, and smaller picometer level errors in the wavefront in order to make what we dig a dark hole. So we move light we move the light from the sun, the star, out of the region of the center of the telescope in order to see the light from the planet. Another way is something called a star shade, and you've all done this. If you hold your hand up, you know, on a bright day to block the sun, you're basically doing a sunshade. Or you bring your visor down when you're driving. So if we unfurl this giant petal-shaped object in space, it may be 30 meters, you know, twice the size of this room, 4 times the size of this room, flying out in space. We put it a really, really far away, and it creates a shadow. And then we fly our telescope into that shadow that blocks the light from the star, and then we can see the planets. Regardless of whether we're using a star shade or a chronograph, it's really still very hard. Is that it depends upon where the planet is when you look at it. If the planet has got its back to you, it's not very bright, you can't see it. If the planet is behind the star, you can't see it. So you need to have the planet over here in order for you to see it. But you know, if it's taking 30 days or a year or more, you got to come back. And every time, and these planets are too faint, and so then you have to come back, and you got to come back and look for it again. And every time it moves. And let's see, this has got. So we've used Hubble to find some planets, and I forget if this has a movie. Nope, this one doesn't have a movie. Okay, but anyway, so this is our Neptune's orbit. So you can see there's some planets that are far away from the planet. Hubble's coronagraph is not very good, and so it can only see things that are really far out, like Neptune and Pluto, things like that. Webb's coronagraph is better, but it's still not great. We are launching a new mission at the end of August, August 31st, I believe, called Roman. It's going to have a coronagraph, and it's designed to look at Jupiter's. So there'll be a lot of good stuff coming up with Roman. And these things, because they're so far out, they've got 100, 200, 400-year orbits. Here's the movie. So this is Hubble data taken over many years. And you can see how slow they're moving. So Hubble launched in 90, and this data, I think, goes to 25. So this is like 35 years of data. The nearest planet has a 45-year orbit. These are all at least 4 times bigger than Jupiter. So this is some Webb data. Now we use the coronagraph. We block the starlight, and then we look at so we find that there's a planet here. So there's the planet, and we look at it at different wavelengths of light in order to figure out what spectrum. So this is at 3, 4, 11, and 15 microns. So this planet is maybe 10 times bigger than Jupiter, and it's maybe 20 times further away. Remember, I said that Webb is better than Hubble, but it's not as good as Roman. Roman is going to look for Jupiter's. Webb can see things like this. Oop. There we go. So this is another Webb data system. There's a bunch of planets here. Based upon the spectroscopy, these planets are rich in carbon dioxide. So they may be forming. They may eventually look a little bit like Jupiter and Saturn, although Jupiter and Saturn have a lot of ammonia in them, as well as carbon dioxide. This is a Saturn twin that Webb found. This planet is similar to Saturn and about the same mass. Alpha Centauri is very close to us. It is the subject of lots of movies and TV shows. It's actually a binary. There's Alpha Cent A and Alpha Cent B. And let's see, this is this planet, I forget, I think this is on Cent A. Yeah, I think this planet is around Alpha Centauri A, and it has a planet around it. It's a gas giant, and it's the closest habitable zone planet we have to us here. And I'm trying to remember, I think, was the Hail Mary Project planet around Alpha Centauri? I can't remember. I think it was. Yeah. So my boss at headquarters contributed towards that book. So these are all the different ways we've looked at habitable planets, or for planets. Oops, back up. So hot Jupiters are big Jupiter-class things that are close to their planets, cold giants. So up here, these are the big planets. This is closer to the sun, further away from the sun. This is where Earth would be, right there. We're finding lots of rocky planets, lava worlds, ocean worlds, giant ice worlds, but we really want to, finding Earths is really, really hard. This is the Kepler menagerie, orrery, and the dates are up here, 2011. So this is the patch of sky, if you will, that Kepler looks at. And those are all of the measurements that they've been making. And you'll see lots of different numbers because the numbers change all the time. So back in 22, we had 5,000, and they were maybe 30% were super Earths, and 30% were gas giants, and 30% were Neptune-like things, and 4% were terrestrial or kind of like us. As of September, we were at over 6,000. This is a fun little animation. This one has sound. I don't hear. Not making sound. I want the sound. I will cheat. Oh. All right, I am on. My sound is turned on. That's disappointing. We tested the sound on the other thing. Yeah. So I will talk it through. I know we had it working when we did it last year. So anyway, what's happening, which you can't hear, is every time it finds a new planet, it makes a sound, a ping. And it starts at 1995, and you can see the rings. And it just, by the end of the animation, it's a cacophony of, and the pitch is related to the size of the exoplanet that it's finding. And I'm really disappointed that's not happening. And I couldn't even get it to play off of the I could, let me take, that didn't seem to help. I'm disappointed.
Don't pull your card, because you'll freak.
Yeah, okay.
I'll fix it. Can you get back into here?
Sure, yeah. It's still not.
Let it play.
Okay. Oh, there we go. that's Kepler. That's Kepler up there. There we go. All right. Oh. Okay, so how do planetary systems get built? They're made up of stardust. And so stars form out of dust clouds in space. The Herschel Space Telescope's found over 700 newly forming stars inside the Eagle Nebulae. The bright blue dots are stars that are forming. This is Webb. This is one of the first release images for Webb. And again, every one of these blue dots here is a star forming. These are planetary systems that Hubble has seen. And so you can see these are, little planetary systems in the dust. So if you want to look for planetary systems, you want to follow the dust. This dust is ubiquitous. And so again, back to spectroscopy, is that this is a very famous system called the Fomalhaut system. And this is the spectra of the Fomalhaut system. This is the spectrum of the Hale-Bopp comet. They're both made of the same stuff, and that stuff is silicon dioxide, common everyday beach sand. This is a Fomalhaut. You can see here's its planet moving. We found it in 04, 06, 10, 12. This is Webb data. This is the planet again taken with Webb. It's inside of this ring of dust. It's just building up and accumulating the dust as it accumulates and gathers up the dust. And then ALMA is a radio wave telescope that's down in Chile, and it's a distributed aperture, and so it can see a planetary system such as this one over here, and that's our planetary system. And so you can see that there's the dust, there's the rings, there's regions of the dust that are getting cleared out by planets. Here's another ALMA image. This little circle here is 1AU. So maybe there's a planet inside there that's about the size of Earth orbit from its star. And planetary dust disks are ubiquitous and diverse. There's lots of them. This one's got a little spiral shape. This one's donuts. Here's some more donuts, rings. There's lots of different ways to form planetary systems. Here's the history of our own planetary system. We started out knowing a few planets, and then we find all of this dust and debris and asteroids. And there's now maybe 800 or so potentially hazardous asteroids that could run into our planet and cause lots of trouble. So there's two real theories as to about how do planets form. One is called the accretion method, where they just circle around and they collect all the dust and they get bigger and bigger. And little things get together to make bigger things, and bigger things get together to make even bigger things. Or this is the gas collapse method, where you circle and you pick up gas and you make the gas giants. This is Ultima Thule. The News Horizon telescope that went out to Pluto flew by this object, and we took an image and again took spectroscopy, and based upon the spectroscopy, these are all the different geological materials that make up this object. It's an asteroid in space out around Pluto, and so based upon all those bits and pieces, it's kind of like a Frankenstein been put together with lots of different parts. So that leads to the accretion model of planet forming being probably the right one. Again, spiral arms can be an indication of a planet. This is the orbit here of Pluto. So you can see this would be Pluto, and there's maybe something forming inside of these spiral arms. This is a direct planet here, and it has a tail of dust. That planet's about 6 times bigger than Jupiter. It's trailing a tail of dust behind it. And the interesting thing is our planet has a tail of dust. So this is our planet here, and this is our tail of dust behind us. And actually, you hear sometimes we have a second moon every now and then. You may have heard that we recently, there's a small objects that sometimes get caught in our orbit and go back around. So the European Southern Observatory, the very large telescope, this is an 8-meter class telescope. There's actually a couple of 8-meter class telescopes, and they've got a coronagraph and called this sphere coronagraph, and this is a bunch of images that they've been taking of planetary systems with lots of dust. This is this is a large binocular telescope image from the University of Arizona out on Mount Graham. Those of you from Tucson or Arizona maybe know where Mount Graham is. I went camping up there a couple of times in my graduate studies. So this is a baby planetary being born. This is an interesting observation. This is a ALMA, did a radio wave, and what it is that when the dust is falling in onto the planet, as the dust is spiraling down and the gas is spiraling down onto the planet, it gives off a radio wave signature. And so they're looking at the radio wave signature coming off of this planet, and it could even be a moon is being formed around a planet. This is another VLT image. A solar system about similar to ours. It's about, our solar system's about 4 or 5 billion years old. This is something about the same size. Planet C is very far away from the Earth, from its sun. There may be more planets, so this is something we're looking at. Okay, so let's talk about habitability. I've used the phrase the habitable zone a few times. So, and I've talked about cold stars and hot stars. So M-class stars around 3,000 Kelvin, our G-class star 5,500, and F-class be 7,500. F, is hotter, colder and hotter. So the habitable zone is the region around the star where you can have liquid water. When you get too close to the star, the water evaporates and becomes steam. When you get too far away from the star, the water becomes ice. And we live in the habitable zone of our star because we have liquid water. And if we didn't, we wouldn't be here. So where does the water come from? The water comes from the star itself. Think about the star as a giant fountain. It's spewing water. This is Spitzer data, and Spitzer is taking spectra. And so here's an image of a star, and jets of material come out of the top and bottom of the star, and this is spectra of water. So the water vapor comes out of the star, goes way up high, freezes onto the dust, and falls back down onto the planetary disk. And this is, say, a newborn star, and you can see the jets. So again, this is a newborn star, and it's shooting a jet out this way, it's shooting a jet out that way of material. Here's another newborn star shooting jets of material out of its ends. Oh, this one actually we did spectron. So this has got molecular hydrogen, carbon dioxide, and silicon monoxide, and they're color-coded based upon the materials. So, like I said, they shoot way up, they collect on the dust, and they fall back down onto the planetary disk. So this is the planetary disk right here, and what you're interested in is where do you have the ice line versus the liquid material. And so when you get really in close, it gets too hot. When you get really far out, it's icy. And with difference, so this is like the snow line at 150 Kelvin of where the materials, and let's see if I, And let's see, I want to think about, right. So I want to talk about this for a moment. It's that water freezes at 0 Celsius. Nitrogen liquefies at 77 Kelvin. Helium liquefies at 4 Kelvin. Carbon dioxide, dry ice, is at -40. So different chemicals, different materials freeze at different temperatures. And so the ice line for different materials is at different distances from the host star. So the water is in a different place. So when it falls down, we develop, that's how you get like a planet like a Jupiter that's a lot of carbon dioxide, because that's where the ice line of the carbon dioxide was. So we have a lot of water, so it's based upon our ice line. And because these things are at different temperatures, we have to study them with different kinds of wavelengths. So the stuff that's really out here that's very cold, we use a sub-millimeter wavelength telescope like the ALMA Observatory. The stuff that's in here in the mid-infrared and the far infrared, we would use Webb, for example. And then the near-infrared down in here, in the visible, we would use Hubble. So different wavelength telescopes can be used to get data at different distances from the planet. And then so ALMA has measured this area out here, and Spitzer gets in the gap in between, and then Webb can look even further in. Let's see, this is one of the interesting things about the ice line is that it creates a dam. And so where you have that ice line, as the stuff falls onto the planetary system and migrates in, it builds up around the dam. So we get this buildup of material. And Webb is observing this release of cold water vapor as icy particles that migrate from the colder zones to the inside of the snow line. And the water vapor acts, it builds it up. So this is actually the mission I'm working on right now. It's called POEM, Planetary Origins and Evolution Multispectral Monochromator. It's going to fly in Antarctica, and it's going to study the snow line in planetary systems and look for the damming effects. We're going to look for snow lines for water, hydrogen, and oxygen in planetary systems by looking again at the spectra. This is another mission that we're looking at. This is going to fly in space. This is called PRIMA. It's a 2-meter class telescope, and it's going to do similar kinds of studies in the infrared. Again, looking at the protoplanetary disk, this is PRIMA's primary science. They want to look at the water snowfall line, the carbon monoxide snowfall line, these icy petal migration into the dam, and to understand how that affects planet formation. And Webb also has been studying this to figure out why comets have silicates, because again, a lot of this fountain of material is silicon monoxide, silicon dioxide, and that's where all of the comets and asteroids get their material. So Kepler, we've talked about the habitable zone. Kepler has identified 100-ish planets in the habitable zone, of which maybe 25-ish are Earth size or within 2 sizes of Earth. There's maybe the most interesting. But just being in the habitable zone is not good enough. Is that depending upon the temperature of your sun, of your star. So this is our star here. Here's our Earth. Is that in this region we have good oxygen behavior. If you go further away, you get into what's called a CO2 toxicity. Mars doesn't have enough oxygen. If you go too close in, and if you get to a close, there's a region here where it's carbon dioxide, carbon monoxide, so it's the chemical buildup. Too close and you have steam, too far away and you have water. But it's interesting, oops, yeah, I already pointed out Mars. There's also an oxygen habitable zone. This is a paper that I forget, oh, I didn't put a date on. I think this is like a 2026 paper. It's a very recent paper, is that the water zone, the habitable zone of water is very broad, but the habitable zone for oxygen is very narrow. Is that if you have too much oxygen, that the amount of oxygen controls the phosphorus and nitrogen values that are needed for life. If you have too little oxygen, then you have too little oxygen pulls phosphorus into the metal. Too much oxygen pushes nitrogen to escape the planet. So you have to have a good balance of oxygen. This is a census. We do censuses of the planets, and we're finding that they're clustered. So this is Kepler 22, and what we're seeing is that we have a bunch that are about one, and they're discrete sizes. They're not continuous. They're sort of discrete sizes. The other thing, and let's see, do I have this one? And I'll talk about this one for a moment. And I'll go back. So size is important. You got to have a big enough planet so that you can have a liquid core. Our planet is big enough that we have a liquid core. Mars is smaller than us. It does not have a liquid core. All right, so question to the audience, why is the liquid core important? What does our liquid core give us? What does our liquid core give us? Yeah. Magnetic field, exactly. The magnetic field protects our atmosphere from getting blown away by our sun. It protects us from being bombarded by radiation. So when the sun gives off a big solar flare and we see an aurora borealis, that's our magnetic field protecting us from cosmic radiation that could cause genetic defects. So yeah, we gotta have the right size. It's gotta have enough mass. Mass also gives us gravity. Gravity keeps our atmosphere. Mars doesn't have an atmosphere. It doesn't have enough gravity to hold the atmosphere. It doesn't have a magnetic field. The other thing that's interesting is that planets orbit in harmonics. I forget, who's the Barkov? Who's the composer of the harmonic of the spheres? Barkov. So our planets all orbit in harmonics of each other. And so we can use that to look for missing planets. And we find that probably every star system out there probably has 1 to 3 planets in its habitable zone. And again, they could be Earths, they could be super Earths, they could be mini Neptunes. One of the interesting questions about is a mini Neptune just a big Earth with a lot of stuff around it? You know, we don't know if a mini Neptune is actually got a rocky center that if you were to blow away all of the methanes and the carbon monoxides and dioxides that you'd have a super Earth or something. But our galaxy, the Milky Way, has, say, 100 billion stars, of which about 17 billion are stars like ours. So there could be 17 billion Earth-like planets just in our Milky Way. But the question is how many of them are in the habitable zone, which not only now means water, but also the right oxygen habitable zone, and also how many of them have moons, and how many of them have Jupiters. So let's start with Jupiter first. Why is Jupiter important for us? Ideas? Yeah? Yeah. Go ahead. Yes. It protects us from comets and the asteroids and things. It sucks up asteroids and comets and things. But there's actually one other really cool thing about Jupiter, is that Jupiter gravity versus the sun's gravity balanced out the amount of iron. The amount of iron in our planet is determined by those two big objects. If there had been no Jupiter, all the iron would have gotten sucked in to the Mercury orbit. but because of Jupiter, the iron that we have in our planet is because of Jupiter and the gravity keeping it there. All right, now, why do we need the moon? No? What's the moon give us? Yeah, you're close. What do you think? Yeah. Tidal forces. Tidal forces, exactly. And it stabilizes our orbit. So the moon acts like an outrigger on a canoe that keeps our planet spinning in a fairly stable orbit. And, you know, a few million years ago, our planet shifted a few degrees, and the Sahara went from a tropical lush forest to a desert. So if you have an orbit that can wobble a little bit, that's not so good. But the tidal forces, I think, leads to life, is the evolution of life in the tidal pools from single cellular to multicellular to, you know, eventual land-breathing people. All right, so what do we need to do life? We're working our way towards life. How do we get to life? So what do we need for life? Natalie Hinkle, she's at LSU. I like her a lot, very articulate. She makes the point that life on Earth is dominated by these 6 chemicals: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. All of the organic chemistry that I never took in college is around how these chemicals interact with each other and make organic molecules. All of these elements are in our star in the same ratio as on our planet. So in order to get the chemistry on our planet with the ratio of the chemistry on our planet, our star, our sun, has to have the same chemicals in the same ratio. So if you want to look for a planet that has possible biology similar to our own, you've got to start by looking for stars that are similar to our own. And each of these is going to have a different spectra. And so what we do is we need to go look at the stars and get the spectra and find out what they're made of. And we can also get spectra of the dust. So these dusts have magnesium and silicates in them. There's polycarbonate hydrocarbon molecules inside this dust. This is some Herschel data of the Orion Nebula, and it's got methanol, for example, and all kinds of sulfur dioxide, hydrogen cyanide, and complex organic molecules that are out there in these dust clouds. Some web data. This has got all of these ingredients here, and for making simple amino acids, including ammonia, methane, and methanol. So Webb is out there inventorying the chemistry of the clouds of dust and beginning the spectra. Let's see, this is a very young planet. I'm trying to remember. It has ethylene, propylene, and methyl radicals, carbon chain molecules. This is a mapping of carbon monoxide in planetary disks. So this is only the carbon monoxide in the planetary disks, and you can see where the buildup is. And this is how we get sort of the organic molecules. The dust grain, remember we said that you get the dust grain and you get the water freezing on the dust, and then these organic molecules come and attach themselves to the molecules, and then we can get spectra on them. So what do we need to have a habitable planet? What do we need to have Earth? We need to have an interior. We need to have a surface. Unless we're all going to be fish and just swim around, we got to have a surface to walk around in. We have to have an atmosphere. And so those are the things that we need to have habitability. Let's say, what is life? That's not really the right question. So we all have, hopefully most of us have children and grandchildren. How do you know that their grandchildren are alive? You know? It's because of what they do. What is it that they do? They poop. You don't look for the crying child, you look for the poop that they leave behind. So we're not going to go find little green men. What we're going to do is we're going to look for the byproducts of the little green men. This is all of the chemical processes that happen on our planet that create energy inside life. All of these produce byproducts. They produce methane and hydrogen and nitrogen and ammonia and hydrogen sulfide and water vapor. And so we're going to look for those chemical signatures in a planet's atmosphere for signs of biology. And actually, the smoking gun chemist is methane. And again, when we do the transit studies and we look at as the planet moves through the atmosphere of the star, so when you get the star, if we take the spectra of the Earth's of that planet's atmosphere, we can look for all the chemicals that that planet has. So this planet, and we can also look at light that gets reflected off of a planet in its spectra. And this is from the transits. Oops. And so here's some spectra that Webb took. Webb has a really good spectrograph, and it's taking planets, and this is water. These are water lines. So this planet is a puffy, it's called like a cotton candy planet. It's a big, billowing, puffy planet. And it's got a lot of water in it, and it's got some carbon dioxide in it. So we're also looking for, this is another planet, but I don't have a pretty picture, that has some methane, but it does not have any ammonia. So this is a water world. It's called a Hycean. It's very hydrogen. It's got a lot of hydrogen, but it doesn't have any nitrogen per se. Here's another spectra from Webb. There you see water, carbon dioxide, sulfur dioxide, and a little bit of ammonia. I think that's, yeah, a little bit of ammonia out there. So we're getting spectra from planets. This is the TRAPPIST planet. And so again, TRAPPIST is around a red dwarf. The red dwarf is not a good place to look. And there may be an atmosphere, but the data is within the noise range. So the brown or yellow would be if there's no atmosphere, and the blue would be the model if there was an atmosphere, but you can see sort of there's a faint envelope with the noise, and we can't make a determination as to whether there is or is not an atmosphere on this one. Earth. So Earth has a very interesting spectra. Venus is boring. Mars is boring. Venus and Mars both have carbon dioxide, but Earth has got all kinds of other stuff. Earth has water and oxygen and carbon dioxide and methane and ozone. And so one of the things, the smoking guns we want to look for is like ozone and methane. The other thing, though, is Earth has not had its spectra, its atmosphere, its entire life. Early Earth didn't have any oxygen. It wasn't until the blue-green algae came along and started creating oxygen. They're all down, you know, there's still some down in Australia I've been to see. But, you know, so the Earth with time had a lot of carbon dioxide and then a lot of methane, and then it built up the oxygen until we get to the atmosphere that we have today. So by looking at it at different points in time, we can get some idea of what's going on. And by the way, this is the guy here, Sean Goldman, is the director of the Astrophysics Division of NASA headquarters, and he provided inputs to the book about the Hail Mary Project. And so this is his pretty picture here about ancient Earth and Proterozoic Earth and modern Earth with different chemical makeup. So if we were to have a really big telescope, we could get spectra of our Earth that kind of looks like this. This is from a study for 2009. But the spectra is actually only one piece of the puzzle, is that if you were to look at our planet as a function of time, what do we have? We have continents. We have oceans. So depending upon what side of our planet you looked at, it would look different. And so if you get a mass of variation up and down, depending upon whether you're looking at land or not land, that tells you something. We have clouds. And if you got a lot of clouds, it's a bright day. You can see that. Whereas with Venus, it's always the same all the time. The other thing is that the light that comes off of our oceans is polarized. I mean, many of you have probably had polarized sunglasses in order to cut down glare when you're out on the water. It's the same thing. The water, scattered light coming off our oceans will be polarized. If we look for that polarization signature, we can tell whether or not a planet's got water. So the next thing that we're working on, I'm on the Habitable Worlds project team right now in the project office, is the National Academy of Science recommended a great new observatory to be launched in the 2040s to try and detect for 25 potential habitable exoplanets by looking for their spectral signature. We are doing this because NASA is the only person we're big enough to do this. The NASA Science Mission Directorate budget is about $5-ish billion a year, $6-7 billion a year. Our budget is bigger than the budget of all of the other spacefaring countries in the world put together. So, you know, that's why we do things like this. This mission could be 10, 20, 30 billion dollars. It depends upon how much money Congress gives us. So this is what a 4-meter system might see. I think a 4-meter is affordable. A 4-meter system is going to be $5, $6, $7 billion. This is what a 12-meter system might see. This one's probably about $25 billion. And so what we're engaged in is we're doing something called exploratory analytical cases, trade studies. So when I started on Webb in 1999, this was what we were thinking about as the straw man for Webb. These are some ideas that came out of industry. This is what flew. And so currently we're working on, we're up to EAC, Exploratory Analytical Concept number 5, but these are the first 3. So this is something that looks a little bit like Webb but off axis. This is something that looks a lot like Webb. This is a smaller version. So these are the segmented mirrors, different concepts. These are all big. They require big tubes to protect them from micrometeoroids. Micrometeoroids would be bad. So here's my last movie. I'm not hearing this. We tested this. It's not muted. You're going to have to play your magic again. We tested this before we came in here. Yeah. We played this.
Yeah, there's no sound.
We played this before we.
But there's no sound loaded on the screen. Yeah, there's no sound on that one.
This is the one we tested when I was here.
Well, but it's not showing sound right now. So it won't work.
unplug that, plug it back in, and
Has nothing to do with my stuff.
How many of gases like oxygen and methane?
there we go.
Possible signs of life itself. And of those, which might above? What secrets do they keep? The stars above. What life as we know it?
There we go.
How many have water vapor? A beacon indicating that oceans might be present. How many have gases like oxygen and methane? Possible signs of life itself. And of those, which might truly have life? After decades of asking, a future NASA telescope could bring us the answers. The Habitable Worlds Observatory is a future mission designed in the tradition of the Hubble and Webb space telescopes. It will use its unique and sensitive eyes to see planets like our own, hiding in the light of their distant stars. Astronomers could then point this mighty space observatory to the most promising planets, those that may hold liquid water. With the help of its coronagraph instrument, which blocks out the dazzling starlight, the telescope will look for undiscovered Earth-sized planets in the star's habitable zone where liquid water could exist. The light from each planet will be split into a vibrant spectrum of colors, revealing clues to the chemical signatures we seek. From there, we can attempt to discover if a planet's atmosphere contains water. And from there, other signals like oxygen or methane. Should all these signs align, the Habitable Worlds Observatory would delve deeper to reveal other hidden clues of life. With further study, we could find signs of sprawling oceans and rugged continents. And if signs of life are revealed,
Interesting. That's weird.
revealing clues to the chemical signatures we seek. From there, we can attempt to discover if a planet's atmosphere
I'm
contains
toggling
water.
between speakers.
And from there, other signals like oxygen or methane. Should all these signs align, the Habitable Worlds Observatory would delve deeper to reveal other hidden clues of life. With further study, we could find signs of sprawling oceans and rugged continents. And if signs of life are revealed, keep a watchful eye for changes over time. This magnificent observatory could discover dozens of worlds akin to our own in its first 5 years. The telescope will gather data on a wide variety of worlds, placing our own solar system in the context within the grand tapestry of existence. And the habitable world in its first 5 years. The telescope will gather data on a wide variety of worlds, placing our own solar system in the context within the grand tapestry of existence. And the Habitable Worlds Observatory will, like the other great cosmic watchers, Hubble, Chandra, Spitzer, Webb, and soon Roman, also conduct a wide range of revolutionary observations of our cosmos, improving our understanding of how our universe led to potentially habitable worlds. Thus, the Habitable Worlds Observatory will help us embark on a quest as grand as any, to tell the story of life in the cosmos, and whether or not we are alone.
Anybody recognize the narrator's voice? John Rhys Davies. So I think some people know him as Gimli from Lord of the Rings. Yeah, it's a fairly famous actor. And I was telling him about the Webb telescope at a conference a few years back before he narrated this movie. And I mentioned to him that my grandmother, that my grandfather came home from Oberlin with, that her parents or grandparents were from Carnarvon in Wales. And so in this picture, he's citing to me a poem in Welsh that is mandatory to be learned by the school children of Wales about the castle of Carnarvon. And yeah, so anyway, at this point, I will entertain any questions.
Thank you for your presentation. I assume from what I've heard from you that we are looking at other planets, stars, solar systems, whatever, that have similar chemical systems to what the Earth is based on. And the life here is obviously carbon, nitrogen, oxygen based. Are we considering that there might also be other life forms, say with a silicon based and maybe an ammonia atmosphere?
Yeah, yeah.
And one other thing, are we still for distant images relying on reflecting telescopes only, or are there other electronic gadgets that are coming online?
All the telescopes we're looking at are reflective, but the question is, are you talking about single aperture or like ALMA, which is made up of multiple telescopes that then combine the signals electronically? So there is some electronic signal processing tricks for making synthetic aperture telescopes from lots of small telescopes. But I want to go back to the bigger question. The science requirements for HAB worlds have not yet been defined, and it's an open debate as to what they should be. There's one school of thought that says we want to look at as many different stars as possible in order to understand all the different ways that planetary systems can come together with regards to M class and G class and L class and K class, anything. And study the whole thing. The people that say we are just interested in finding a second Earth, they're more looking at just the G-class stars with the right chemistry and the right makeup. The question then becomes, how many are there? So of the planets that are like ours, and of the solar systems that are like ours, there may be a dozen that we can see. Maybe. If we look at a whole bunch of different kinds of stuff, now we're looking at multiple dozens, 20, 30, 50, 60. So if you, it's an open question. It also has to do with the size of the telescope. And I think I answered, oh yeah, the final question, life. So if you go back to the movie, the Hail Mary Project and the character Rocky. All right, how many people seen the movie? How many people? So Rocky that is based upon a life form that actually exists on our planet in the deep sea, at the thermal vents of the deep sea. And it was my boss at the guy, so I am fully funded out of NASA headquarters, and so technically my boss is Sean Donegal Goldman. His contribution to that book was to tell the author about, he is an astrobiologist. He studies the idea of biology on other planets, and he explained to the author of the book about this life that lives at the bottom of our own ocean and how it's made up of different chemistry and organism and things like that. But at the same time, I want to say that every single living thing on this planet has the same DNA. Everything on this planet has the same DNA. It can be a single chain, it can be a double chain, it can be a triple chain, but it's all the same DNA. We're all hosts of a giant virus called DNA. The interesting question is, I think it's a really compelling question, is there DNA on other planets in our solar system that is different, or is every DNA on every planet in our solar system the same? I don't know. But back to your question. So Sean Donegal Goldman, his contribution to the book was to point out to the author that life can look pretty bizarre and still function, and that it's based upon these organisms that we know exist on this planet. So next, yeah.
Hi, great talk. Thank you. I noticed in all of your graphs where you're identifying exoplanets that pretty much the smallest ratio I think you showed to size of Earth was like 0.8. Are you interested in looking, or is NASA generally interested in looking at objects that are smaller than Earth, or
we probably can't see them.
Is that like just a limitation?
I mean, we're having a really hard time building a telescope to see things that are Earth size, and to go smaller, it gets even harder. Yeah, it's just money. But sometime maybe in 50 years, what we'll do is we'll put two big telescopes and create an interferometer and be able to see small stuff. There's kind of a risk, as we're waiting for the question back here, there's kind of a risk. The scientists always want to ask lots and lots of questions, and the problem is we can't necessarily afford to answer lots and lots of questions. So there's this constant struggle between what the scientist wants and what we engineers think we can build versus what we think the Congress will give us the money to do.
Two things. Number one, that thing that you showed early on that covered the star so that it blocked the light, kind of like a artificial eclipse, and you could still see the planets. Is there enough light still being emitted even after that thing is over there to be able to see, to show the planets?
Yeah.
Because they don't emit light themselves.
No.
Okay.
The the light coming off those planets is a reflected light from the sun,
Right.
their star. And we have to block 10 trillion times of the light of the star to see the planets.
Okay. And the other thing is, does the radio astronomy place down at Green Bank, do they have anything to do with this?
Well, other than the fact that it fell down and doesn't
Yeah.
Yeah.
But at the time.
Yeah, at the time. I think that the Green Bank is 21 centimeter wavelength, and that's a different wavelength than this. This one is more like, I think there was a telescope. I don't know. That's a good question. No, let me think about this. The radio velocity work is in the visible. The chart that I showed the example of that PEG 5 was found was on a 3.6 meter telescope in Chile. So the radio velocity work, I had to scroll back inside my head. The radio velocity work is done in the visible, not in the radio wave. And actually we've been doing some radio velocity work with the Keck telescopes out in Hawaii. There and then over here. Go ahead.
I have two. The first one is I have never understood radio telescopes, and I want to ask how they work, and do we actually get pictures from them or something else? My second question is, on my Facebook feed, there are videos that come through, and there's a man who talks as if he has been in contact or has seen or talked with beings from other places. Should we believe him?
I actually was asked to interview for a classified position to look into that. And in the interview, they asked me, why do I want to do the job? And I said, because I think it'd be a lot of fun, and because I'm a skeptic, and I'm a critical thinker, and I'm likely to find lots of explanations for the phenomena that they're reporting. But the problem is that I was funded to be doing other work, and one of the people on the interview panel was my boss at headquarters, a different guy who's now higher up in the organization. And I said, but I'd be willing to do it, but I'm only willing to do it half-time because I got this other work to do. And they said, thanks, but we need a full-time person. There's a lot of interesting videos and photos and things that are coming out from that are being released, that are part of that study. So that the results from that study are coming out. They're basically showing bright, shiny objects that behave funny. There was an interesting video of somebody trying to shoot something down. I don't know what they are. I don't know what they are. I also want to point to what President Obama said the other day, is that he thinks that there's other living things out there in the universe, but he's never seen them. He's never seen any evidence for them. And what he then clarified is that the universe is such a big place that there must be something somewhere. But as I tried to point out on here, is that the odds of finding something are very small. The habitable zone of water, the habitable zone of oxygen, having a Jupiter, is that it may be, the old expression, takes a village to raise a child. It may be that it takes a galaxy to raise a civilization. And the question is, how many civilizations are there in our galaxy? 1, 2, 5, 6, and how long do we last? And at any time, do two civilizations overlap at the same time? Yeah, so I tend to be very skeptical, want to take a big grain of salt. I'm a trained scientist. I am trained to say, where's the data? Is that if you want to make exceptional claims, you need to have exceptional data. So if you want to claim something, where's the data? That was, I think, the second question. And the first question is, how do radio wave, is that they're basically gigantic dishes that, like the one in Greenbank and the one down in Puerto Rico, is basically a single pixel. It's just bringing in a single pixel of data and looking at it. There are other dishes in the Netherlands that is made up of a lot of rays. If you remember, I showed a picture of the ALMA with lots of multiple telescopes that put together and pull data together. You do the same thing with, you can have radio wave antennas where you have big antennas and you can pull things together. And so it's almost like the same way radar works. Radar can make a pretty picture by scanning and looking at the back reflection. So think about it as a reverse radar. Is instead of taking a single antenna and scanning and looking at the back reflections, you have lots of antennas that are collecting signals in order to build up an image. Okay.
Okay, and one last question.
Over here, yes.
Thank you so much for coming. I hope you make Lakeside a return spot for you. So appreciate your insight. My question is, how much of the information that you're gathering year by year is shared with the folks who are trying to contend with global warming, because we're told that excess carbon dioxide is probably the most critical threat to our atmosphere. And yet with all the data that you seem to be accumulating, it would seem we'd have a much better handle on what global warming is manageable by our maneuvers or techniques, and that which is not within our power to control. I mean, we've looked at 25,000 years since the Ice Age. Well, something has been occurring much longer than the automobile hit the streets. And my question, I guess, is how much of the information you have is being shared with the folks who are trying to find solutions to slow the process of global warming?
So NASA has something called a Science Mission Directorate, SMD, and inside of SMD we have the Astrophysics Division, which is basically we're looking out. And then there's the Heliophysics Division, which is studying our sun. And then there's the Planetary Science Division that studies our solar system. And finally, there's the Earth Science Division that studies our planet. And one of those things that studies our planet, like we have things like the Landsat satellites, and we have the weather satellites, and that feeds into NOAA. So one of the things that we built and we're getting ready to fly is something called the carbon. It was the Carbon Observatory, but I think it had three-letter extra. And the idea was we're going to fly this satellite and we're going to look at the spectra of the carbon to figure out what is the age of the carbon that's getting burned. And we can tell if it's coming from coal, or if it's coming from oil, or if it's coming from exhausts of automobiles and things like that. So we were going to fly that mission, and the previous incarnation of the current administration killed the mission because they didn't want the data. So the current administration is not collecting any data to inform their policies with regards to climate change because they don't want to have data-driven policy. But there is overwhelming, irrefutable data that climate change is happening and it is accelerating. And it's accelerating over the last couple hundred years or so. Is that the most interesting? For a while I was kind of on the fence, and then about 15 or 16 or 20 years ago, I saw a study on the acidity of the ocean. The ocean is absorbing CO2 and is becoming more acid at a very rapid rate, which is causing the bleaching of the corals and the things like that. You know, the ocean, think about the ocean as a very slow sensor, and it's picking up carbon rapidly. So that's a real problem. And then if you look at some of the products that have been put out by the NASA used to have a client study office in New York City at Columbia University that got shut down by the previous incarnation of the current administration because it's producing data. We are, every year, we're setting new temperature records. We're having new heat waves in Europe. Australia's having heat waves. Every year is a hotter and hotter and hotter. And one of the things that's happening with it getting hotter is more water is evaporating, which puts more water into the atmosphere, which makes torrential rainfalls. You know, just here at Lakeside, in the last couple of years, we've had some fairly, heavy rainfalls that were unusual. Is that the occurrence of 100-year floods is no longer 100-year floods. They're now 10-year floods, you know, so the climate is changing, and it's changing more rapidly. But my side of the house, we look up, we don't look down.
Thank you very much, Phil. Thank you.